Hey everyone, so today's video is going to look at using a general linear model approach in order to look at multiple predictors on a single outcome. And we're going to do this in a few different ways, but specifically focusing on using one of those predictors to control for some variable. And we're going to be doing that with multiple numeric predictors. So 2 numeric predictors on a numeric outcome, which typically would have been called multiple regression. We're also going to look at the effect of a numeric predictor and a categorical predictor on a numeric outcome, which might have traditionally been called ANCOVA, or analysis of covariance. And finally, we're going to look at a quick example of 2 categorical predictors on a numeric outcome. And this may have been referred to as the factorial ANOVA or two-way ANOVA that you might have heard of in the past. But we're going to use a general linear model approach, and you'll see that we can use the same structure to do any of these different combinations. So let's get right into my R screen and get at it. So again, because I'm going to be providing some figures in the panel behind me, I'm going to pop myself up a little bit higher here, and this will allow us to see everything a little bit better. So I'll open up a new script file here, R script, and I'm going to use options SciPen equals 999. Not 000, because I like to have R not give me scientific notation for its output. And we're going to use the flexplot package. So I've got to use that. I've got to load that up using the library command. So we'll do that with library flexplot. If you don't have flexplot installed, you may need to go back to my visualizations video to check out how to do that. Okay, now that we've got those the package loaded up and everything ready, we want to basically use one of the data sets that's actually included in the flexplot package that's actually called income. So we'll have a look at what that looks like using the view command. So we're going to view income. Now, when we see that, we basically have essentially a few different variables here. We've got income, before and after, what type of schooling you've done, how many hours you've put in, or how many hours you work, what group you're in, and what your stats skills are. So the first example we're going to be looking at is predicting your income after schooling as a function of your stats skills. But we want to control for the number of hours that you work, because we see these different amounts of hours are going to lead to different kind of income as well. But we want to look at the independent contribution of stats skills. So we need to control for the amount of hours you work, and we'll see how we do that. So typically, when we get a data set, we're going to want to look at the univariate visualizations to make sure there's no problems with the data. If you need to get into that, have a look at the visualizations video and a couple of the other videos when it goes through that. We're not going to bother here because I know that these data sets are okay and there's no problems with them that we need to worry about at this point. So we're just going to get straight into looking at these data and trying to figure out how we're going to control for that variable. So let's use the flexplot command. And we're going to look at income underscore after. And that's going to be as a function of stats underscore skills. And data equals income. All right, so if I do that, I'm also going to use the method equals quote LM. So this will show me what my linear model would look like roughly as well. So if I do that, that's essentially what we're looking at. But what we do know is that our income is not only going to be affected by stat skills, but it's going to be affected by the number of hours worked. So we could actually have a look at that by taking the same command, and we're going to add another factor here, plus hours. Now, if I do that, what we see is now we've got 3 lines. So if we've got this 11 to 23, negative 11, I'm not sure how you actually work negative 11 hours, but that's okay. 23 to 37 or 37 to 71 give me these 3 different lines. What we see from this is that these give us different values. So we want to make sure that we're controlling for that, or removing the influence of that first and looking at the independent contribution of the stat skills. Now, another way we can do that is by using the bar in the middle here. So stat skills bar, or that means paneled on hours. And this will just break that down in 3 different ways. So what we can see is stat skills, your income as a function of stat skills. When you've got low hours, sort of medium hours, and high hours. So it looks like they're slightly different, but we're going to have a look at that in the actual analysis. Now, remember, we can always go back and look at this first one to see what it looks like overall, but that's not controlling for the number of hours. So we need to do that. So what we're going to do is create a model. I'll just call it M. And its structure is going to look similar to this. So it'll be LM of income underscore after as a function of hours plus stats underscore skills, comma, data equals income. Now, what you can see here is up here, I actually graphed it using stats skills first and then hours second. And here I put hours first and stats skills second. Now, in this case, when we've got multiple numeric predictors, it actually doesn't matter what order you put these in, as you'll see in the output. But the thing is, when we get to categorical variables, it's going to matter what order you put them in. So you may want to get into the habit. So the way it works is it's going to give us the effect of the second variable here after controlling for the first one. That's the way it'll work later on, but in this case, it actually doesn't matter, and you'll see that that's actually the case. So if I run that and create that model, I get a linear model. We can do a summary of our model. And what we see in our outcome here is that we've got an estimate here, and this says basically our income is expected to be in thousands of dollars, I believe, 30,000, and that is basically when there's 0 stats skills and 0 hours. So it doesn't really make a lot of sense. But we just need that to make the calculation. And then what we see is there's an increase of $0.37 thousand for each increase in hours and an increase in income of $0.382 thousand for each increase of 1 in stat skills. So what this is saying is that we are increasing this much. This is the independent contribution of stat skills after controlling for hours. So basically, we don't care about this effect here. We see that it's significant, but we don't care about it if we are controlling for that. What it's doing is it's removing the effect of hours to give us the independent contribution of stat skills. Conversely, it's also removing the independent contribution of stat skills and giving us the independent contribution of hours. So it works both ways in this case, but it depends on our research question and what is the hypothesis that we're actually testing here. And ours here is, how does stat skills change your income? Or what's the relationship between stat skills and income? Now, another thing that this does is it gives us multiple R squared. So this basically tells us that the model overall accounts for 28% of the variance in the data. So that's all pretty good right now. That's all we need to know about this data right now. So pretty good. This is a fair amount of data that it's giving us. We can have a look at the diagnostics by using the visualize command of M. And if I do that, I'm going to pop this out because these graphs are a little bit small here. Make this a little bit bigger. And what we can see here is that my histogram of residuals looks pretty good. There's a little bit of maybe bimodality in it, but it's not too bad. It's mostly symmetrical, no major outliers. My residual dependence plot shows there's not really any problem in here. A tiny bit of curve in the middle, but nothing that I'd be too concerned about. And then the spread location plot, the line looks relatively flat. Remember, the rule of thumb might be something like the lowest end of the bar and the highest end of the bar should not be a multiple of 4 times or so. If it's bigger than that, maybe you need to consider something about fixing your problem that you have with heteroscedasticity. So doesn't look like there's any problems with the data right now. One of the other commands that's built into FlexPlot is the estimates function. And so we can use estimates of M, and this will give us a little bit more information. So remember how we got our model R squared, which was 0.281. We saw that before. This also gives us a semi-partial R squared. And what this means is it's giving us the R squared of each of those independent contributions. And again, we're interested in stat skills, and we see that after controlling for hours, stat skills accounts for 14.6% of the variance in the model. We also get our estimates that we saw in the summary above as well. Now, finally, if we actually wanted to plot what the model looks like after controlling for hours, we can use a different function included in FlexPlot called added.plot. And what this does is it will basically do a plot that controls for one variable. We use the same structure as we used in this model here. We'll place it in there where hours is first and stat skills is second. And we're also going to use method equals LM. And when we do that, what we see is we've got income after predicted as a function of stat skills after controlling for number of hours. And we can see that now we still have this increase up here that goes between, in this case, about 50 all the way up to just about 80. All right, so let's do an example where now we look at a categorical predictor on a numeric outcome, but we've got a numeric covariate that we want to control for. And we're going to use the exercise underscore data set that's included in FlexPlot. So what we might want to do is look at the influence of therapy type, whether that be cognitive therapy, behavioral therapy, or control, which is no therapy, on weight loss. So we can plot that by using FlexPlot, weight.loss as a function of therapy.type, comma, data equals exercise underscore data. Now, if I run that, we get a figure down below me where we can see that we've got a few different amounts of weight loss depending on your different group that you're in, cognitive, behavioral, or control. But what we know is that motivation might have an influence on your weight loss as well. So we might want to control for that. So we might have different levels of motivation, and we might have just gotten some really motivated people in the cognitive and behavioral groups and really unmotivated people in the control group. So we want to control for that potential factor. So what we do is we can actually have a look at the effect of that. So we could look at weight loss as a function of motivation plus therapy type. And then we're going to use method equals LM. And what we can see here is that, yes, indeed, it looks like motivation, as motivation goes up, weight loss also goes up. It looks like it's pretty similar across the three groups. So we do want to control for that just to make sure that it's not having an undue influence on our estimates of what the different therapy types did. So now what we can do is create a model of that. Now, remember I told you that when we're using a categorical variable, the order of the variables that you put into the model matters. So in this case, we're going to create a model. We'll call it M again here. And into that, we're going to do an LM. And it's going to be the same thing that we've got here, right? So basically, we want to look at the influence of therapy type after controlling for motivation. So motivation is going to want to go first. So we're just going to do this part of the command and put it in there. So weight loss as a function of motivation plus therapy type data equals exercise data. That should create me a model called M. Looks good there. Okay, now the next thing we may want to do is have a look at the model diagnostic. So visualize M. And when I do that, I'll actually pop this out because it'll be easier to see the different diagnostic plots. What we could see is our histogram of residuals looks reasonably good. Our residual dependence plot looks like it's reasonably flat, which is good. And our spread location plot looks reasonably flat as well. So no problems with the model here. We may want to look at a summary of the model. So summary of M, what we see is the output that that gives us, because we've got multiple values or multiple predictors, isn't as useful as when we've got a single predictor. So instead of this, maybe in order to get an idea of what the overall effect of the model is we can use the ANOVA command. ANOVA of M. What this does is it will give us an effect, an overall effect of therapy type, which basically says our F ratio is 11.406 with the degrees of freedom of 2 and 196. And our p-value is 0.0000206. So very small. So basically what this is saying is there's a large effect of therapy type on weight loss after controlling for motivation. Now, it matters what order that you put these in because of the default way that the ANOVA command works. And I'll show you that in a second. So the next thing we may want to do is actually now look at our added plot function, which is the same as we used up here. So I'm going to copy and paste that, and it's weight loss. It's this command here. So it's easy just to copy paste things, and I don't need method equals LM as an idea. There we go. So weight loss as a function of motivation plus therapy type, data equals exercise data. And now what we see is when I plot that, we've got weight loss as a function of therapy type after controlling for motivation. And remember, these are medians and quartiles, and you could plot means and standard deviations if you like differently. Another thing we may want to do is now see if there are differences between these different groups after that controlling for that. So as we saw earlier, we can use the estimated marginal means function. So if you don't have EM means, you may need to install it. Or if you do, you'll probably have to load that using the library command, means, EM means, load that library. Okay, so it's loaded. And now what we want to do is use that function EM means of M, which is our model, and pairwise as a function of therapy.type. Now, what we can see is now it's looking at and giving us our estimated marginal means after controlling for the amount of motivation. So our estimated marginal mean is 3.96. Our estimated marginal mean for the cognitive group is 7.67, and for the behavioral group is 7.68. So you can see the difference between those actually shown below. Now, if you saw the previous video that I made on the general linear model method to do an ANOVA with categorical variables with more than 3 levels, you'll see that these values are slightly different. And that's because we've now controlled for a second variable in motivation. And then we can see whether or not these contrasts are significantly different from one another. So here we've used the Tukey method to control for multiple comparisons. And in my previous video, I talk about the different methods that you could use. So you may want to look back at that as well. We see that the difference between the control and the cognitive group is significant. The difference between the control and the behavioral group is significant. The difference is negative 3.728. And the difference between the cognitive group and the behavioral group is not significant. In fact, the p-value is almost 1, 0.9998. All right, the last thing we could possibly want is looking at the independent contribution of therapy type on weight loss. And we can use the estimates function that's built into FlexPlot to allow us to see that. So we've got a model R squared. So the whole model accounts for 21.6% of the variance. But the semi-partial R squared, or often known as partial eta squared as well, basically breaks it down by each of the different factors. So in this case here, we see that therapy type counts for about 9.1% of the variance. We also get our estimates of our means again, and the mean differences as well as Cohen's d's, and the estimates for the numeric variables that really aren't as useful, but that's okay. Now, remember I told you that it's really important to put the variables into the model in the correct order. And that's because of the way that the ANOVA function in R works by default. But if you want to have a look at the difference between the ways of calculating sums of squares, type 1 sum of squares, type 2 sum of squares, and type 3, you can actually use this link that I'll provide here, and I'll also link it below. So you could have a look at that, and it sort of gives you the example of how to do that. If you don't want to do that, you don't want to worry about putting the variables in whatever order you want, you could actually use a different ANOVA command. It's capital A ANOVA, and it's included in the CAR package. So the CAR package is companion to applied regression, CAR. And if you don't have that, you're going to want to install that package using your regular method and then load it up. So library, CAR. Of course, I got to spell library correct first. Library, CAR, and run that. So it's loaded up that library. And now what I'm going to do is actually create two separate models to show you that it actually doesn't matter which way we go here. So I'm going to copy this model that I had up here. I'm going to call it M. So we've already got that model built there. I'm going to create a new model called M2. And I'm just going to change the order of these variables. Now, therapy type plus motivation. Now, if I look at M2, now I've got that created. Now, if I use the regular ANOVA command of M, we're going to look and see what this says. What we see is we've got these p-values here that are 0.7215 and 2061 or something. And if I use an ANOVA on M2, we see that those values are quite different. They're still both significant, but it would matter in other conditions. But we see that this actually gives us very different predictions. Now, that's because of the type of sum of squares that's calculated by default with the ANOVA command. But with the CAR package, you could use the capital A ANOVA. So ANOVA of M, and then we specify type equals 2, and I get that output. Now I can look at the same thing, ANOVA of M2, and when type equals 2, we see I get the exact same p-values, 206.011, 206.011, 1978, 1978. So in this case, it didn't matter which order I put these in, and allows me to specify that I'm going to be using the type 2 sum of squares. And the type 2 sum of squares is especially useful when we're controlling for things and there's no interaction present in our model. We'll get into interactions in a future video. All right. So lastly, what we're going to do is we're going to look at what would typically be called a factorial or two-way ANOVA. And we're going to use a GLM approach again, looking at a numeric outcome with two categorical predictors. So what we're going to be doing is we're going to be using a data set that I'll be linking below. It's called weight change. So we're going to need to load up that data set. So I'm going to do that by using the read.csv command, or you can import your data set however you like from wherever it is. I'm going to put it into an object called weight, and I'm going to do a read.csv. Mine is located under data, and it's called weight, capital C, change.csv. All right. And I typically will say strings as factors equals true. Okay, so now I have a new data set up here behind me called weight. It's a data frame. You should see 27 observations of 3 variables. It's hidden behind my head here right now, but you should see that. So if we have a quick look at that data set, so I'm going to view this data set, and it's called weight. We see we've got weight change, and then we've got 2 categorical factors here. So age group, 20s, 40s, and 60s it looks like, and exercise intensity, moderate, low, and probably high. Okay, so looks like we've got a few different values. So we're looking at this weight change variable. So the first thing we would probably want to do is look at those univariate variables, see if there's any problems. I know there's not really anything there, so I'm not going to worry about it right now. But what we'll do is we'll look at the bivariate plot, what we're really interested in. Now in this data set, what we're really interested in looking at is weight change as a function of exercise intensity. So I'm going to plot that. Flex plot, weight.change as a function of exercise underscore dot intensity. Data equals weight. And when I do that, what we see is we've got a fairly large range for the high exercise intensity, moderate, and low, but it looks like we essentially have more weight change for higher intensity and less weight change for a low intensity. But what we know is that maybe age group actually has an effect on your weight change as well, and we want to control for that. So we can actually plot this in a couple of different ways. If I just copy this command and paste it, and now I do that, but I panel it on age group. So it's age.group. What we see is, yeah, the pattern looks basically the same, but there's less and less weight change as we get older. So we may want to try and control for that. So the first thing we'll do is we'll create a model. Again, we'll just call it M because it makes my life easier and I make fewer typing errors. And again, remember what we're going to want to do is put our control variable first, and then our second variable, which is exercise intensity, is the one we actually care about. So we're going to look at it. We're going to look at LM of weight change as a function of age group, because that's what we're controlling for, plus exercise dot intensity. And data equals weight. So now when I create, I obviously made, I made a couple of spelling errors here. Let's try this again. Plus exercise intensity, data equals weight. Okay, so I might want to visualize to make sure there's no massive problems with the model. I will actually zoom that out so we can see. So again, our histogram of residuals looks reasonably normally distributed. There's weirdly nothing in this one bin here, but that's okay. It's not too bad. Our spread location plot looks pretty good. It's reasonably flat. Remember the high end of the line is, no more than about double, maybe 2 times or just slightly over what the bottom end of the line is. So it's reasonably flat. I'm not too worried about heteroscedasticity, especially with a sort of small n that we've got here. So looks reasonably good. We could use a summary of this, but again, remember we saw in the last example that that's not really as useful as what we've seen previously. So what we can do is use the ANOVA command, again on M, and what we see is we get an effect of exercise intensity, and again, this is after controlling for age group. So remember that we put age group in first, and now we've got the effect of exercise intensity after controlling for age group. We don't care about this effect that we've got here. And what we see is there's a significant effect. We could also use the added plot function to be able to visualize that and see how it's different than the original graph that we created when we didn't actually include the age group factor. So if I do that, added dot plot, and it's going to be this same command here. Weight change is a function of age group plus exercise intensity. Data equals weight, and we'll just have a look at that. Now, what we can see here is that it appears that these error bars are now much smaller than what we had originally. And we can see that right up at the top here. I'll reload this graph. This is the one we use with weight change as a function of exercise intensity without including the factor age group here. And when I show you that graph again here, we can see how the spread is so much larger here. So when we controlled for that, so we have exercise intensity as our groups, and we look at weight change while controlling for age group, we see that we've got this nice grouping now after controlling. So one last thing we may want to do is look at the estimated marginal means. So we can look at the EM means. Now we've already loaded up our package as we saw earlier. We're going to do EM means, M, comma, pairwise as a function of exercise dot intensity. And of course, what it gives us is our estimated marginal means of high being 1.24, low being 0.74, and moderate being 1.04. Now, again, what I've graphed here is these are medians, but we could just use the different command, adding the plot type being standard error or standard deviation if we want to see those actual means plotted. But that's fine. We can see what the actual numbers are, upper and lower confidence intervals, and the contrast between them showing which pairwise comparisons are significant. And we see in this case, all three pairwise comparisons are significant after using the Tukey method for comparing the different groups. All right, so hopefully that gives you a really good intro into using the general linear model method to look at multiple predictors, whether that be multiple numeric predictors or a numeric and a categorical predictor, or two or more categorical predictors for being able to control for one of those variables when looking at the effect of another variable. All right, we'll see you in the next one.